So here for chapter 9, we talk about many electron atoms. So right past the hydrogen atom, we go to one with more electron system. So we'll talk about Schrödinger equation. Okay. Hartree-Fock method, that's kind of a Schrödinger method used for this chapter. Okay. And the term symbol related to energy states. Okay. And within here, we will talk about wave function as well. So again, we follow the pattern. For a microscopic system, we talk about energy levels and wave functions. Okay. So the first one about Schrödinger equation, and I want to emphasize here, to set out the Schrödinger equations for many electron atoms and for molecules are required. Okay, there might be a problem in your final exam asking you to write out, the Schrödinger equation. Okay, so it's pretty important for you to understand the concept. So here it's quite straightforward if you understand the concept. Okay. So the first one I want to mention something about, just mention the atomic units here. So in this chapter and in chapter 10, when we ask you to write a Schrödinger equation, usually we will ask you to express the Schrödinger equation in atomic units in order to simplify your expression. So in our textbook, table 9.1 gives you the atomic units and its corresponding SI units. Okay. So if we ask you to write atomic units or something in atomic units, you simply need to just define all these things equals 1. Okay. For example, the mass of the electron equals 1. The charge over proton, E equals 1. Okay. Those Bohr radius equals 1. Okay. Also simply just define them equals 1, and will greatly simplify your expression. And we will see the examples here. Okay. So the question is, how can you write the Hamiltonian operator? That's a key part for you to step up the equation, okay, the Schrödinger equation. For the Schrödinger equation, all the things you need to care about is the Hamiltonian operator. How can I express that? And then the following steps will be really easy. Okay? So this is actually the hard part. Well, to set up your Hamiltonian operator, you first need to be clear about some of the operators. Okay, we know Hamiltonian operator is a total image operator. It consists of potential image operator and kinetic image operator. So those are the two things you need to be clear. For example, the kinetic image operator, right? In SI unit, we learned in chapter 3, actually, we used from chapter 3, frequency. This is the kinetic image operator in SI units. But we can also simplify into atomic units, right? Because in atomic units, the mass of the electron, if we assume this is the electron, okay, the mass of the electron equals 1. H bar, H over 2 pi, the reduced Planck constant is also 1. So we can reduce to this. Okay. Potential image operator due to attraction. I just remember the form. The formula is like this. It's actually with a negative sign. And here the Z is the atomic number of the nucleus. Okay, for example, you are writing the hydrogen atom, actually Z equals 1. But if you write helium atom, Z equals 2. Okay. And reduced to a compact form using atomic units, you will see actually the E, what I mentioned before, equals 1. Okay, 4 pi epsilon naught is also equals 1. Okay, the permitted, I think it's due to something, permitted something, okay? Like this one, so it greatly reduced to this ratio. Same thing for electron repulsion term. Okay, can you tell me what's the sign of this repulsion term? Is negative, positive, or 0?
Isn't it positive?
Should be positive. Okay. So similar forms as attraction term. So the difference is we first we change the sign to positive because simple repulsion can increase your energy, not decrease your energy, right? Make your system more unstable. So that's why it's a positive term. And next one is here, the R means the distance between the electrons with the nucleus. So here we're talking about repulsion, so that's actually the distance between the two electrons. Okay, and again, E equals 1, 4 pi epsilon 0 equals 1, you reduce to this form in atomic units. Okay, any questions? Those are the basic blocks we need to know in order to construct the Hamiltonian operator. Okay. But let me give you a real system. So lithium atom. So here, this subscript represents the atomic number. Okay, Z equals 3. And simply by writing the lithium atom neutral, so it should have 3 electrons here. Okay. The first way to do is just count the number of each energy form, as we did last time. Okay, we count the energy form for hydrogen atoms. So here we just need to count the number of energy terms for many electron atoms. Okay, so can you tell me how many kinds of energy are in this system? In general, how many kinds of energy? Let's say one by one. The first energy you can think of is what? Kinetic energy of what?
Electrons.
We have two things here. One is the nucleus, another one is 3 electrons, right? So when you talk about kinetic energy, actually you can refer to 2 kinds of kinetic energy. One is the kinetic energy for the 3 electrons altogether. The second one is the kinetic energy of the nucleus, right? This is actually the first 2 energies. Can you think of other energies? Potential energy. Okay, when you say potential energy, also refers to 2 kinds of potential energy. One for attraction, one for repulsion. So there are actually at least 2 energy forms here. And for each energy form, what you need to do here is to count how many that energy is in the system. For example, the first one, kinetic energy of the nucleus. We omit this one because we actually will assume, usually we'll assume the nucleus is fixed because the nucleus is actually more massive than electrons. So it can vibrate a little bit, but compared to the kinetic energy of electrons, it's way less. So we can actually omit this or neglect this one. Okay, it's the same as result, but at least you will see for this kinetic energy we have one term in this group. This is the kinetic energy of the nucleus here, where we omit it. Okay. The second one that you mentioned, kinetic energy of electrons. So how many kinetic energies of electrons we have in the system? 3. Okay. Potential energy due to electron nucleus attraction. How many terms? Potential energy due to attraction. How many? Attraction means one electron attract with one nucleus, right? And we have 3 electrons, so there will be 3. So those 3 attractions. Potential energy due to electron-electron repulsion. This is a little bit hard, okay. 2, 3. So if we label the electron 1, 2, 3, actually we have 3 pairs of repulsion. So 1, 2, 2, 3, and 1, 3. Okay, so we have also 3 pairs. That's the first step you need to do. So this tells you that for your Hamiltonian operator, if you assume the nucleus is fixed, you will have 3 plus 3 plus 3, 9 terms in your Hamiltonian operator. So when you write out the Hamiltonian operator, you can actually check whether yours makes sense or not. So not at least, you must have 9 terms in your Hamiltonian operator. Okay, so the next step is to write out all those 9 terms. Okay, so set up the Hamiltonian operator. We have the 3 groups. And for this one, we know 3, this one 3, this one 3. So what are the 3 here? So remember, I introduced that the kinetic energy operator looks like negative h-bar square over 2m Laplace operator, right? And here we have 3 of them. And usually, for lithium ion is okay, but think about sodium ions, or sodium atoms. 11 electrons, and you want to write this forming 11 times, add them together. So instead, we introduce the summation sign to simplify your expression. Okay, especially useful for those atoms with more than 3 or 4 electrons. Okay. So can everybody read the summation sign? We use your basic math. Okay, the sign is you add all the things with respect to I here, and from 1 to 3. Okay. Next term, particular energy due to electron nucleus attraction. We know attraction term I also told you. Something like that, right? From the Columbic law. And here we only need to substitute z equals 3 because here the atomic number is 3. And again, we can use summation sign to simplify our expression. And repulsion, right, with 3 things. And so this is straightforward. Again, if we have the sodium atom with 11 electrons, we also want to use summation sign to simplify it. But pay attention, here you will actually you sum all the things with respect to not only I, but also another term, J. It's about 2 electrons. So the expression is a little bit different from here. So we need 2 summation signs. One accounts for I, one accounts for J. And here pay attention to 2 things I label in red. The first one is the sign should be positive, but the first 2, they are negative. The second term is here. I did not say J equals 1. Instead, I say J is larger than I. Okay. This is because if you say J equals 1, when you do the summation, you will do something like that. So 1, something like 1 over R12 plus 1 over R21, something like that. But actually, these 2 terms represent the same repulsion energy between electron 1 and electron 2, so they can only be counted as 1. So simply means if you write J equals 1 here, you actually double count some terms. Okay, so instead I define J as larger than I, then I can get rid of this problem. So let's say if you still want to say J equals 1, you think this is easier for you to understand, then please divide it by 2. Okay. I can show you actually. I did not send you the handout, but I actually derived it. And you can also, I'll give it to you as an exercise. You can just go back and derive. Why do you need to divide by 2? Okay. You can simply try this. J equals 1 to 3, I equals 1 to 3, and you do it. You will find actually compared to this term, let's say this one has 9 terms, this one has 18 terms. So that's why you divide by 2 to eliminate those terms which are double counted. Okay? So either of the forms is okay. Which one you want to use depends on you. Okay, but just pay attention. Repulsion term here is a little bit weird compared to the first 2. Okay? So any questions about this? And we have to check. We have 3 terms here. We have 3 terms here. We have 3 terms here. So actually that makes sense. Because while we analyzed before, there are 9 terms in Hamiltonian operator, and indeed we have 9 here. Okay. So next, so this is actually the key steps. Okay, I want you to everybody be clear. At least if you are in my section, you have no problem in your homework programs. We have 2, approximately 1 question asks you to set up that equation. Okay. But for everybody in my section, you can now do it. So this is the key part. So after this part, what you need to do is just set up the Schrödinger equation pretty easily. You have 3 terms of kinetic energy, combined with 3 terms of attraction terms, combined with another 3 terms of repulsion. Right? Those are the 3 we wrote before. And what you need to do, this is your Hamiltonian operator. Include the operator on wave function equals E times wave function. That's your Schrödinger equation. Okay. And based on this expression, actually, somewhat, if you are really careful, you will tell here we do not consider about the LS coupling. Okay. Usually, when we ask you to write the Schrödinger equation, we only ask you to write the general form. You don't need to consider about LS coupling. But if you need to consider about that, you just need 1 more term here, which you can find the equation in the textbook. It's something we showed you in the last homework problem set as well. Okay, it's just with one more term here. But anyway, in most questions, we will just ask you to write the general form. General form here, without considering errors coupling, without considering the magnetic field. Okay? Or you can write this expression in atomic units. So you compare this one with this one, after you will find those equations in atomic units are way easier. It's actually, right? It's clear. It's more clear than this one. Okay? So usually that's why in order to make up the grading becomes easier, we'll ask you to write your expression in atomic units, usually. Okay? So any questions? Any questions? Okay, for now, let's do one exercise. Please set up the Schrödinger equation for oxygen ion. The anion with 2 negative at the charge. And given part of the periodic table there. I can just write in atomic units, so simplify your expression. And of course, when you use summation sign, right, to shorten your expression. Source on one, I'm already finished, and actually correct expression, pretty good. Or some of them maybe some minor mistakes, right? So the first thing is I want to ask you some questions before you sit on the things. What is the Z value? 8. 8 or 10? 8.
It's a nuclear charge of oxygen.
It's a nuclear charge. So it does not affected by, or not, it's not affected by the number of electrons. whether you have 10 electrons, you have 8 electrons, you have 6 electrons, whatever, Z will still be 8. So how can you tell Z equals 8? Where did you find it?
Periodic table.
The number 8 is actually atomic number. Z is 8. Okay, also the number of protons inside of the nucleus is 8. So that's right. Z equals 8. So that's the first thing I want you to be clear. Okay. Second question. How many electrons? How many electrons here? 2 negative, right? So 8 plus 2 equals 10. So this is the first thing you need to be clear. Before you counting the number of inner terms here, you need to be clear. We have 10 electrons. So after the kinetic energy and the attraction energy should be 10. Both should be 10. Okay? So that's the term. So compare with yours. That's correct. Sort of things you need to, so easy to make mistake. First thing is here. It should be 10. Okay. Second mistake is 8. Okay, not 10. And sort of things here. So don't forget there are 2 summation signs here. Or you can use atomic units like this. Okay? For this case, you can either write it this way, for this term, I mean repulsion terms, or you can say J equals 1 to 10, but remember divided by 2. Okay, or you just do this way. Okay, so any questions? So in theory, we can give you lots of other electrons, sorry, the atoms or actual ions here. So let's make a summation here. For Schrödinger equation, the fourth Schrödinger equation should be like that, okay, in general. So the first terms here represent the kinetic energy of the nucleus. So we're talking about the atoms or the ions after just one nucleus. There's only one term. And there's a number of x means number of electrons. So there are x terms of kinetic energy of the electrons. There are x terms of attraction energy terms. So attraction energy terms here, the upper bound for the summation line, the summation here is the x, actually the number of electrons. But here z is the atomic number, z. Okay. And there are still terms for repulsions in atomic units like this one. So in general, we have these 3 kinds of particles we can write in the Schrödinger equation. And for atoms, can you tell me what's the relationship between z and x? Z equals x. And for ions,
It would be Z, or X is greater than Z.
so what's the relationship between z and x? For anion, in general, ions. Z is
Less than X.
Ex minus ni is equal to z.
well, we just find the equality, do not find the equation. In general, z is less, more, or equals
Less.
less than x. Cations, right? Okay, so what we practiced before is anion. Those are oxygen anion, so z is smaller than x. Okay. So reflex here, this number will be different from this number. But for atoms, those numbers are the same. Okay. And usually, if you omit this part, it's okay. Okay. We do not need to say explicitly that the nucleus is fixed. Okay. You can just assume without saying that it's okay here. Okay. But don't assume that electron kinetic energy is 0. Okay. Don't omit this part. You can skip this part is okay. But at least you need to show us. Okay? So any questions? So that's the Schrödinger equation. Okay? Based on the Schrödinger equation, once we can solve it, we will get wave functions and energies. Okay? But here, unfortunately, as you can see what we talked before, we need to use the approximation method to solve the Schrödinger equation of many electron atoms, and later for molecules. Okay. The reason is why? Can you still remember? why we cannot solve the Schrödinger equation analytically for these two systems.
You never know exactly where two electrons are in relation to each other.
Or something is due to what term? Inter-electronic wave function. Right, recall from last section, which said for helium atoms, this repulsion term is actually the troublemaker. And here, for lithium atoms, for many electron atoms, we may have more than one troublemakers. So they prevent us solving the Schrödinger equation analytically. So instead, in chapter 8, we introduced the vibrational method, which is kind of one of the approximation methods we can use. So here, we introduced the Hartree-Fock method. It's kind of one of the vibrational methods as well. They use it. Okay. So for Hartree-Fock method, I know the exact procedures for carrying out the Hartree-Fock equation for the Hartree-Fock method is sort of complicated. So definitely will not require you to do this from the beginning to the end. But we want to make sure to understand some of the concepts in this method and some of those important conclusions we derive from the derivation. Okay. So the first thing is the algorithm of Hartree-Fock method. General picture should be good. Okay. We start with something, we guess trial wave function, right? Like last time I told you, the vibrational method, the beginning part is we need to find a trial function. But how can you find it? Simply just guess. Use your sense to guess. But make sure this trial wave function satisfies at least the boundary conditions, or at least it can be normalized. Okay, those things that scientifically value trial functions. And go into this Hamiltonian operator. And your textbook for helium atom, these two terms, okay, the two terms here can be expressed in this way. Okay, and of course we will ask you to do the evaluation of this, so here just for your reference. And you solve the Schrödinger equation, you can get a new wave function. The Ci here comes out. Okay, so the next step is you need to compare whether the newly obtained wave function is sufficiently close to your trial wave function you put in. Okay, if your answer is no, let's say it differs quite much, please return to this step. Use the new wave function as the trial wave function and go this step again. So this process is called the self-consistent process, and that's why Hartree-Fock method is defined as self-consistent method. Okay, so you keep doing this until your answer is yes. You feel it's comfortable. You feel satisfied that your newly obtained wave function is sufficiently close to the function you put in, and you will output the wave function, and based on the wave function, and based on Schrödinger equation here, you get the approximate energy.
How do we know that it's closer?
Depends on you. So if you compare the ratio of the two wave function, or somehow you feel like, either way I think you can do is to get the energy for each time, and you will find the energy difference becomes less and less, less and less, unless the two energies approximately equal to each other. Then you can say or reach the steps. But when you reach the limit, you can get your trial wave function here. Out from here, you get the wave function, and you get the energy from this equation. But as you can see, all those things are based on the trial wave functions. They are approximate. So the wave function you get here is also approximate wave function and approximate energy states. Okay. We cannot get the exact one because we cannot solve the Schrödinger equation exactly. And then that's the end of this method. So that's actually the general picture for Hartree-Fock method. So based on this flow chart, actually you can see the mechanism is the same as the vibrational method. It's just one of the specific case for vibrational method. Okay. So the wave function here we use to solve the many electron atoms actually is not like some general or some common wave functions that you saw before. So here we use one called the Slater determinant. So although this is the name of determinant, actually it is the determinantal wave function. So some of you will think, oh, why this one does not, this phrase does not contain the word of the phrase wave function here. But why we say we use Slater determinant to do the calculation? Well, Slater determinant just means wave function. Okay. And to set up the Slater determinant, again, is required. Okay, is required. So it's necessary for us to know how can we set up the Slater determinant. So in general, for an atom with n electrons, your Slater determinant should be n times n in dimension. Okay. General form is like this. Have you ever had linear algebra before? Not all of you, right? If you haven't studied the linear algebra, please find a textbook and just do the self-study with related to determinant, because this is really important too in chapter 9, 10, and 11. So if you are unable to solve the determinant, then you are unable to give the wave function and energy. Okay? So please, I noticed that some of you haven't started the linear algebra, but it's the time to pick something up. Okay. For those who used the linear algebra before, it's good. Just do a review. Okay. So anyway, this is the determinant. So usually use two lines. It's not bracket, okay, but not parentheses. Now do not use that. Just two vertical lines. And what we did before, like vertical line squared, same thing. Okay. So the first thing here, there's a constant in the front of the determinant is defined as the normalization constant. Okay. It's a wave function, so this part looks weird, but it's actually a wave function, so it still contains normalization constant here. Depends on the number of electrons. Okay. This one, the C1 is actually the spatial wave function. There is something like when you draw the energy levels, so when you do the electron configuration, the one line there, remember in your Chem 1B class, say this is 1s, sorry, 2s, is 2p orbitals like that, right? This line is actually the spatial wave function there, or it's one orbital. This alpha is the spin wave function. Okay. So reflect on this picture is you have two. So each orbital contains two spin orbitals. One spin up, one spin down. So when you spin up, it's alpha state. Spin down, beta state. Okay. So those are actually the two letters here represent the location. And the number here represents the electron. So the physical meaning is electron 1 is in C1, the C1 orbitals and alpha spin orbital. The picture is like that. Okay, this is the physical meaning for the first term. And if you compare the one column here, you will find all those orbitals are the same. Right, psi 1 alpha, psi 1 alpha, psi 1 alpha. So they have the same orbital but different electrons. Okay, and if you compare with one row here, each line, their numbers here n, 1, 1, 1, 1. The electrons are the same, but the different locations or different orbitals. Okay, that's how you set up your Slater determinant. So the first thing is you need to be clear about your electron configuration. That's the first thing. And then use this language to describe the location of the electrons. And then use this conclusion. So each row, so each column represents the same orbital but change the electron. Each line has the same electron but change the orbital to construct all your n times n determinant. And don't forget about normalization constant as well. Okay, so clear about that? This is required and it's very important. It's a really popular question in chapter 9. Okay. So if no questions, let's do one exercise. Please write down the Slater determinant for the ground state of barium atom. So what's the dimension of the determinant? 1 times what? 4 times 4. Okay. So at least you, not at least, you must have 16 terms. Well, we can just write the first element in each column and first element in each row, and then use dots to represent the others. Okay, it's okay. You don't need to write all of them explicitly. To be clear about the electron configuration of the ground state of barium atom, right? You're telling me what's the electron configuration? So 1s, 2s, 2p something. That's your electron configuration for ground state. If you're in an excited state, this one electron can go whatever you want, right? 3p something. But here we want to talk about ground state, so that's the only choice. So that's your electron configuration. And actually you can convert this one to the physical picture. 1s orbital, 2s orbitals. They each one have 2 spin orbitals. And this is alpha, beta, alpha, beta. And for alpha state, we can fill in the 4 electrons. Spin up, spin down, spin up, spin down. And that's actually the configuration. Right, and based on this configuration, we know we have 4 electrons, so it should be 4 times 4. And the first term will represent the first electron in the first place. And we know the first place is 1s orbital. So that's psi 1s. Alpha spin orbital here, alpha spin orbital. Fill in the first electron 1. That's the first element, right? And we know for each row, for each line here, they represent the same electron but different orbitals. Right? So the second one is actually this orbitals, psi 1s, beta 1. And use this, you can do the other 2. Okay? And for each column, circle. Right? It's easier than each one because each column represents the same orbital but different electrons. So all the thing you need to do is just change the number here. 2, 2, so here will be 3, it will be 4. And then use the same argument here for each term, you can write here, here, here. Okay. And last, don't forget about normalization constant. Okay. This equals what?
4 times 3 times 2.
24 also works. Okay. So if you just give the factorial here, it's okay. Or you can evaluate it, still okay. But make sure your calculation is correct. Okay. And in your textbook, actually, in order to simplify this expression, you will not use psi 1x, instead you just provide 1s. And that still works. Okay? That simply represents orbital here 1s. Okay? But you should be clear, this is not a orbital notation. It's actually the real wave function there. The wave function for 1s orbital. Okay? Any questions? So again, this is required, and make sure you know how to write it for other atoms. And based on what you will see, usually we will not give you the atom with 11 electrons or 10, because 10 by 10 you have 100 terms. Okay. Or sometimes we can do it by just telling you, please write the first element for each column and first element for each line, and then other part we know you understand. Okay, so that's the same. So that's all. Okay. So based on the Slater determinant, we derived another postulate. This is the last postulate we encountered in this class, which says wave functions should be anti-symmetric. So anti-symmetric, the definition is if we have 2 electrons, and if we switch the sign of either 2 electrons here, they will change, switch the location, they will change the sign. So a more general conclusion is something like that. So if we have 1, 2, 3 until n. So if we switch either 2 of the electrons, for example, I switch the 3 and 2, they will change the sign. You switch either 2, they will change the sign. So if I change 3 and 2, I change the sign. But now if I change 1 and 2 again, the sign will change back to positive. It just means you switch the position of either 2, change the sign. Switch again, change the sign. Okay? And this is a special case with just 2 electrons, so will be like that. Okay. So this can be easily proved by using Slater determinant as a wave function. For example, the psi 1, 2. So here it talks about Slater determinant for helium atoms, like this, right? And we can expand it in this way. So here, again, I want to remind you, everybody should be able to do the expression using linear algebra. Okay. So not that hard, actually, just use this diagonal line minus the product of this diagonal line. Okay. And what happens if we change the position of the 2 electrons? So now we get 2, 1. So we also change the position here, right? And we do the expansion again. And can you see this one is actually the negative of this one? Can you see that? Satisfy this relationship. Okay, clear? And why do we need to do that? This is based on the experimental observations, and more importantly, it satisfies Pauli's exclusion principle. Okay. So Pauli exclusion principle says, from European 1B, these 2 electrons cannot occupy the orbital in this way. They cannot occupy the same spin orbitals. Okay. So let's use Slater determinant to check what will happen. If the 2 electrons are in the same orbital with the same spin directions, what we saw before, 1, 2, now alpha should be equal to beta, because the two electrons are in the same spin orbitals. Right, so alpha equals beta, so our Slater determinant becomes like this. So before, here is beta, here is beta. And here the same, because we assume alpha equals beta, so all betas are alpha now. And based on the Pauli exclusion principle, we know this will cause something weird to happen, right? Because it violates the Pauli exclusion principle. So let's say what will happen if we expand. Get 0, right? What happened? The wave function vanishes. Probability 0, or simply means the system disappears. Or in other words, this system disappears simply because you force alpha equals beta. And now Pauli told you they cannot be the same. So alpha cannot be the beta. So if you do this way, you end up with 0 as your wave function. Simply means no system there. Violates Pauli exclusion principle. Okay? Make sense now? So only by doing so, by constructing the Slater determinant, can you satisfy the Pauli exclusion principle. And also, the thing is, if you use the Slater determinant as your wave function, naturally your wave function is anti-symmetry. So that's the logic here. So in order to satisfy Pauli's exclusion principle, we developed the Slater determinant. And by writing the wave function as Slater determinant, we naturally satisfy the postulate number 6. Okay, so can you hear about that? So that's the wave function part for many electron atoms. Okay, any questions about wave function part? Okay, if not, second one, energy. So for the energy, I don't have many things to talk about. So because Hartree-Fock method is also a specific, not original method. So the same conclusions obtained as the original method, that is, the exact energy should always be less or equal to the energy obtained by Hartree-Fock method. So here is Hartree-Fock, the non-hydrofluoric acid. So Hartree-Fock. So then we define the correlation energy and the difference between the exact energy with the Hartree-Fock energy. So naturally there will be this relationship. Okay. Either be a negative or equal to 0. Okay. And again, once E exact equals EHF simply means you get the right eigenfunction. Okay, you just use the right eigenfunction to do the measurement. You get they are equal to each other and correlation energy is 0. But this is impossible for real calculation. So if we want to approximate some energies for many electron atoms, it's impossible for you to get the eigenfunction. But it's possible for those systems. We can solve the Schrödinger equation analytically. For example, polynomial box, or we already know the eigenfunction, right? But if you want to play the game, you can just put your eigenfunction as a trial function into this method, and you will end up with the exact energy. Okay, so that's the logic here. Is there any questions?
So HF is just like the energy you calculate
From Hartree-Fock method.
Okay.
Approximating energy.
And then what is the correlation?
It just means the difference. So E correlation is defined as the difference.
So would we be given the E correlation if we're solving for E exact?
No, because you first know E exact and then you know E correlation.
Oh.
So if we give you correlation, simply indicates we know the exact energy. Yeah. It could be a product, but in practical, in practice, it's impossible. Okay. So any other questions? So last part about term symbols. We already talked about in hydrogen atoms, so here hopefully it will be easier. In general form, we mentioned last time, 2s plus 1, L, J. Alright, what's the name for L? And what's the name of L? Capital letter L. Here. Total, good. Total what?
Total orbital.
Total orbital.
Angular momentum.
Angular momentum. That's all. Two words. Quantum number. Okay. J. Total. Angular momentum. S. Total spin. 2s plus 1, my question. What is 2s plus 1?
Total spin multiplicity?
Just spin multiplicity, okay, almost there, without total. Okay. So 2s plus 1 defines as spin multiplicity. And that's why, for sometimes if this is 1, we call singlet. If 2, we read as doublet, 3 as triplet. So we have 1, let's say 1s, it's like singlet s. Okay, 2s, doublet s. Okay, that's indicates the spin multiplicity. And the symbol for L, different values correspond to different words. And selection rules, again, the same. The same as hydrogen atoms. What we introduced in hydrogen atoms chapter is actually a general convention. Okay. Also true for many electron atoms. And for molecules, we have another set of selection rules, which we'll talk about in 11. Okay, but here, this works for every atom. Okay. So how can we derive term symbol? Again, this is a popular question you will have in your final, or at least on your quiz. To derive a term symbol for many electron atoms. We have already derived the term symbol for hydrogen. Okay, so here it's just a little bit different. So first we need to find the total orbital angular momentum, L. Okay, the quantum number L. So I should also put quantum number here. The quantum number L. Well, the total orbital angular momentum, by definition, can be obtained by doing the vector sum of all the orbital angular momentums from every electron. So let's say if you have n electrons, you just sum, but here is vector sum all the orbital angular momentum from each electron together, and that will give you the total angular momentum. Okay. Or you can do this way. You first calculate the capital letter ML, the magnitude orbital angular momentum quantum number first, by here is a scalar sum of all the ML from every electron here. This is a scalar sum, this is the vector sum. Okay. So once you get that, you can derive the L, the magnitude here really refers to the magnitude, equals the maxima ML value. Okay? So the picture is like this. Let's say we have 3 electrons. Each one has an orbital angular momentum as I1, I2, I3. And they are vectors. So if you want to do the vector summation, you need to connect them through this way and where capital letter L is. So this capital L is vector sum. But if you project them to the z-axis, the sum becomes scalar. So you have the first one, you have the second one, you have the third one, and L. So also LZ. You want to calculate the total one, you simply add them together. That's a physical picture of the orbital angular momentum here. And same thing for total spin angular momentum S. Okay, you have the 2A. You either might do the vector sum or you do the scalar sum doing this way. Okay, calculate the MS first. And then find the maximum MS, then we give you the S number. And we have now L and we have S. What we need to find out is J. J, possible values like this we talked last time. And also LS coupling, due to LS coupling we do this way, right? From L minus S to L plus S with an interval of 1. So that's the possible values for J.
So L is like the S, the P, the D.
Yeah, L is like this,
Okay.
what I showed before the symbol.
So when you have like the L1 or I2, I3, are those like the 1S, the 2D, and then the...
No, that's not. That's for the single electron. But here you talk about 1S, 1D is combine them together.
Okay.
What term symbol is the capital letter L is combine those things together and then assign a letter.
So those are different electrons.
Those are different electrons.
Okay.
Different electrons. Well, this is actually lithium atom. 3 electrons here. Okay. So here I want to ask you a question. In order to derive the term symbol, we have actually 2 kind of groups, 2 kind of methods. One is do the vector sum, one is do the scalar sum. Which one you want to use to derive the term symbol? Which one is very good for deriving term symbol here? think about vector sum. And think about the questions you encounter. Have we talked about the direction of each orbital
No.
angular momentum? So how can you do the vector sum then? Of course you do the scalar sum, right? You know the ML for each one. You simply sum them together, that will give you calculator M. And you find the maximum M for this configuration, and that will give you, for that configuration for that group, then you will get the calculator for that group. Okay, remember last lecture on Friday, we derived the term symbol for S2, for P2. And for P2, we did a lot of tables, those things. The basic idea is clear. Okay. We first find out the MS, ML, and then derive L and S. Once you get L and S, J is pretty easy. From L minus S to L plus S with the interval one, that's all. Okay? That's how we derive it. So let's do my exercise. Please derive the term symbols for the electron configuration S1 and 2. Okay, let's do it together maybe. So we have this electron configuration, right? We have S and P orbitals, and each one has one electron. So how can you assign the two electrons into the two orbitals? I'm also be thinking this way, right? With the two electrons spin up. Can we have another situation? Those kind of things. One up, one down. Okay, because the electrons are indistinguishable. So if you switch the position of the two, it doesn't matter. Okay, if you switch the direction to both up, to both down, it doesn't matter. So we actually, at least we have two situations. So you will end up with two term symbols that indicates. Okay. So we'll not have time to derive all. Let's derive the term symbol for this one as an example. So to derive that, we told you the first one you need to find out the ML. Right? ML equals ML1 plus ML2. So this equals what? So what's the ML for the S orbital?
0.
What's ML for P?
Plus or minus 1 or
0 plus minus 1. Right? So if we add the two together, we actually end up with this. Right? But what's the L value then? L value equals the ML maximum. Right? What's the maximum for ML?
1.
Okay. Next one, MS equals what? MS1 plus MS2 is equals what? Spin up, MS equals what?
It would equal 1.
Right? Spin up,
1
half.
1 half. 2 spin up, right? Equals 1. And what is J? Oh, sorry, we need to divide S first. S is what? MS equals 1, S equals J equals 2. 0, 1, 2. Okay. So the term symbol is what? L equals 1 is what letter? P. String multiplicity, 2s plus 1 equals 3. J value 0, 1, 2. That's the term symbol for this group. Okay. In the same trick, you can do this group. Okay. So this one, this will end up with just multiplicity as 1 here, string multiplicity. Okay. So we call those things as triplet sets. This thing has a singular state. And they are related to the fluorescence and the phosphorescence, the question in your homework. Okay? So we have the two things, and you need to find out. So this is the quantum number for each electron, and you find the capital letter ML, capital letter MS, derive capital letter L, capital letter S, derive capital letter J, derive term symbol. Okay, compared to higher decimals, you will see actually it's a little bit difficult, but the general idea is the same. Okay, the spring up 1/2, spring down make it 1/2. The L value is the same. Okay, L and L value, all the same with Hund. Okay. So based on term symbol, we introduced the Hund's rules. The Hund's rules is to tell you how can you tell among all the term symbols of one configuration which one will have the lowest energy. We have three rules here. So the first one is the state with the largest S has the lowest energy. So simply here, triplet state compared to the singlet state, triplet state will have the lower energy. Second rule tells you if the two term symbols have the same S value, then you compare L. The one with the larger L has the lower energy. Okay? So let's say we have 3P, we have 3D. Which one has the lower energy? This two, which one has the lower energy?
D.
Because L for this one, capital letter L is 1, capital letter L here is 2. Okay. The rule 3 says if having the same S and L values, let's say if the two are the same, we have 3P, 1, 3P, let's say this is 3. Alright, they have the same L value as the same S value. How can I tell which one has the lowest energy? Well, Hund's, the third rule tells you you need to compare the value of J. But for J, you have two situations. One is that if the electron is less than half filled, then we choose the smaller J. If the electron is more than half filled, we choose the largest J as the lowest energy. And the priority of the three rules are actually 1 is higher than 2, 2 is higher than 3. Okay? So here some of you may have a question about what is half filled, right? So let's do a table here. For each orbital, S, P, D, F, whatever, we'll have completely filled situation and unfilled situation. Okay, for S orbital, how many electrons we need to completely fill the S? So 2. So then half filled just means more. Okay. For P, how many electrons we need? 6. So half filled means 3. For D, 10. So half filled is 5. For F,
14 and 7.
14 and 7. So if something with P2, that means less than half filled. If with P4, means more than half filled. If P3, just half filled, you either choose. So if it's just at the half filled, the J value will also be the same. I think it's just one J value, so you don't need to really care about which one has the lower energy. You choose either largest or lower. The largest one or smallest one. They will be the same J there. Okay. So that's a Hund rule. And based on Hund, you will be able to tell which one. Let's say with our carbon atom. So carbon atom, I just imagine it's a make carbon thing. Carbon atom, which one with the lowest energy? The carbon atom configuration is.
So it would be 3P0.
Less than half filled, right? We will choose the
Smaller J value.
smaller one. Hey, that's smaller one? Well, I cannot remember. Anyway, you just go back and check the third rule, right? The third rule says less than half filled is choose the lower one, right?
Yeah.
So that should be the. Yeah, should be the. But anyway, memorize the three rules. Will not give you in the equation sheet. Okay. And what we need the term symbols. Well, again, is to label electronic energy states for many electronics. For example, the scientific paper, when you write a paper, you describe the behavior of the emissions for some transition elements. And how can you tell other scientists that this transition involves that two energy states? Well, did you see that? The left. Term symbol switch one. Right. This one is from this state to this state. This state, see S orbital. So S state to I. So I is actually with higher quantum numbers, with really high L values. Okay, those things. So this is actually a language for scientists to communicate with each other. Right? We represent this term symbol to tell. It's better than you to say, oh, this transition is from the fifth excited state to the ground state. Right? But if you end up with many electrons, many inner states, it's really inconvenient to say it's from the sixth excited state to the second excited state, instead of just saying from this term symbol, from this inner to the inner state. Okay, and show you the term symbol. And everybody understands the term symbol, so if you see that, we know which one is higher, which one is lower. Okay? Any questions? Again, this part is required. Okay? So happy Thanksgiving!